Hello everyone, my name is Namrata Verma, Assistant Professor in the Electronics and Telecommunication Department at Sri Santosh Rungta Group of Institutions, Rungta College of Engineering and Technology, Bhilai, Chhattisgarh. Today we are going to discuss one of the digital modulation technique named as Quadrature Phase Shift Keying or QPSK. In today's lecture, we cover the topic with the following points. First, we see the objective of this lecture, then introduction to digital modulation, then the introduction to PSK, that is phase shift keying, then basics of QPSK, QPSK modulator, QPSK demodulator, then advantages and disadvantages of QPSK with application of QPSK, and at the last we will see the conclusion. Now, let us see the objective of this lecture. The first objective is to educate learner on the fundamental principles, technical details and practical application of QPSK as a digital modulation technique. And second objective is to provide a clear and comprehensive understanding of QPSK, including its advantages, implementation and role in the modern communication system. Now, let us see the first, introduction to digital communication. In case of digital communication, there are two major constants. The first one is the bandwidth and the second one is the transmission power. And whatever modulation technique we will use should have a low transmission power and should have low bandwidth. When we transmit digital data over a bandpass signal, it is necessary to modulate the digital data onto a carrier wave. The digital signals are in the form of pulses. When these pulses are to be transmitted over a communication medium, its shape gets distorted. Therefore, the communication medium must have a large bandwidth. Practically, we use the telephone line as a communication medium for sending digital data from one place to other. These communication take place through a local area network like LAN or wide area network WAN. The telephone lines used for such application do not have sufficient bandwidth to transfer the digital data without distortion. Therefore, we cannot put the digital data directly on the telephone lines. Thus, it is necessary to convert this digital data into some kind of analog signal so that the bandwidth requirement can be reduced. Therefore, to achieve this, we use certain modulation techniques which are amplitude shift keying, that is ASK, phase shift keying, that is PSK, and frequency shift keying, that is FSK. Let us see first ASK, that is amplitude shift keying, that operates on the principle of transmitting two different amplitude of a sinusoidal carrier corresponding to logic state 1 and 0 in the digital data. For digital data 1, we transmit the carrier signal as it is, and for 0 simply we will transmit 0. In binary frequency shift keying, that is BFSK system, sine wave of two different frequencies are transmitted corresponding to logic state 1 and logic state 0 in the digital data. For logic state 1, high frequency will be transmitted, while for logic state 0, low frequency will be transmitted. In binary phase shift keying, that is in BPSK system, phase shift of sinusoidal carrier is switched from one value to other corresponding to change over from 0 to 1 or from 1 to 0 in the digital data. Before understanding the quadrature phase shift keying, first we understand what is PSK and how a PSK signal is expressed in terms of energy and power. Phase shift keying, that is PSK, is a digital modulation technique which convey the message signal, which is digital data, by changing the phase of carrier signal. The PSK modulation technique is widely used in wireless LAN, biometric, contactless operation along with RFID and Bluetooth connections, etc. There are different types of PSK modulation depending upon the number of phase shift or how many number of bits are being transmitted at a time. Mainly there are two types of PSK. The first one is binary phase shift keying, that is BPSK, and the second one is quadrature phase shift keying, that is QPSK. In BPSK, one bit is modulated or transmitted at a time. In this technique, the carrier signal takes two phase shift such as 0 degree and 180 degree. It is also called as two phase PSK or phase reversal technique. BPSK is similar to double sideband suppressed carrier modulation scheme, but here the message signal is in digital form. But BPSK signal have some drawbacks, which are it has low data sending rate and having low efficient, or it is less efficient. To achieve more data rate, we transmit 2-bit data at a time as in QPSK. For BPSK, that is for 1-bit transmission modulation scheme, the modulated waveform can be expressed by S of t, which is equal to S of t is equal to A cos of omega ct when we transmit bit 1 and A cos of omega ct plus pi for transmitting bit 0. As we know, the mean square value of the cosine waveform is given by the formula, that is P is equal to A square upon 2 pi integration from 0 to 2 pi cos square omega ct dt, where A is peak amplitude and P is signal power. Now, we apply a simple trigonometric formula here, that is cos square theta is equal to 1 plus cos 2 theta by 2. Now, apply this formula in the above equation, then power will be P is equals to A square upon 2 pi integration from 0 to 2 pi 1 plus cos 2 omega ct upon 2 into dt, or it can be written as P is equal to A square upon 4 pi, which is multiplied by integration of 1 from 0 to 2 pi plus integration of cos 2 omega ct from 0 to 2 pi dt, or after substituting the limit we can write it as P is equals to A square upon 4 pi, which is multiplied by 2 pi minus 0, as we know that cos of 2 omega ct integration from 0 to 2 pi dt is equal to 0. Then the outcome of the above exercise will be P is equals to A square upon 2, or A square is equal to twice of P, which can be also written as A is equals to under root 2p, or which is equal to under root 2 e upon t. As we know, power can be represented as energy upon time. So, here E represents energy and T represents time. So, amplitude A can be also written as under root 2 E upon T. Now, we can represent the expression of PSK wave in terms of power by replacing the A by under root 2p. So, the expression will be S of t, that is equal to under root 2p into cos of omega ct for bit 1 and under root 2p into cos omega ct plus pi for bit 0. As we know, cos omega ct plus pi is equal to minus of omega ct. Therefore, the expression of S of t becomes under root 2p cos of omega ct for bit 1 and minus under root 2p cos of omega ct for bit 0. As there is 180 degree phase shift, therefore, it is called as phase shift keying. And in terms of energy, the above expression can be written as S of t, that is equal to under root 2 E upon t cos omega ct for binary bit 1 and minus under root 2 E upon t cos omega ct for binary bit 0. Now, let us see the basics of QPSK. Quadrature phase shift keying, that is QPSK, is a form of PSK in which two bits are modulated at once, but in BPSK one bit is modulated at once. In QPSK, instead of transmitting one bit of data, we are transmitting the group of 2 bit together and we are selecting one of possible 4 phase shift to pass the information. It select any one of the 4 possible carrier phase shift, that is 45 degree, 135 degree, 225 degree and 315 degree. Out of this 4 phases, it will select any one phases or any one phase shift in carrier. Later, I will explain how one of this phase shift is selected. QPSK carry twice information as BPSK using same bandwidth. So, here we can increase the data rate by QPSK. The reason is that here we have 4 phase shift in QPSK, while in BPSK we have only 2 phase shift, that is 0 or 180 degree. In QPSK, bandwidth is reduced to half as compared to BPSK. This is because in QPSK, 2 successive bits in data sequence are grouped together. It is bandwidth conserving scheme which is example of quadrature carrier multiplexing scheme. Quadrature carrier scheme is analog scheme, while quadrature phase shift scheme is digital scheme. In BPSK, when symbol changes, the phase shift of carrier is changed by 180 degree as there are only 2 symbols. But in QPSK, 2 bits are combined together and this combination form 4 different symbols which are 00, 01, 10 and 11, and when these symbols changes, the phase shift of 90 degree will occur. The generalized expression for QPSK signal can be given as S nt or S of t, that is equal to under root 2 ps cos 2 pi fct plus phi t, giving it equation number 1, where phi t is phase angle and which is equal to 2 m plus 1 into pi divided by 4, where m is equal to 0, 1, 2 and 3 as we have 4 symbols, and Ps is symbol power. The generalized expression for QPSK signal can be also expressed in terms of energy, which is given by Snt, that is equal to under root twice of Es divided by Ts into cos 2 pi Fct plus phi t, giving it equation number 2. As we know, power is equal to energy upon time, and where Es represents the symbol energy and Ts is symbol duration. As phi t is equal to 2m plus 1 pi upon 4 for m is equals to 0, 1, 2, 3. Therefore, after substituting the value of m, the phi t will be pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4 respectively. And as we know, by the trigonometric formula, cos A plus B is equal to cos A into cos B minus sin A into sin B. Now, applying this trigonometric formula in equation number 2, then that equation becomes S of Nt, that is equal to under root twice of Es upon Ts whole multiplied by cos 2 pi Fct into cos phi t minus sin 2 pi Fct into sin phi t, giving it equation number 3, where phi t represents the phase angle, which could be any values from pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. From this equation, we can observe the following points. The QPSK signal can be composed of two orthonormal functions phi 1 t and phi 2 t, as the angle between the cos 2 pi Fct and sin 2 pi Fct is 90 degree. That is why it is calling as orthonormal function. Therefore, we can express the QPSK signal in terms of two orthonormal basis function. The specification of orthonormal function is, first, they have unit energy, and second is they possesses 90 degree phase shift with each other. It is clear from the expression that the angle between cos 2 pi Fct and sin 2 pi Fct is 90 degree. Therefore, they are called as orthonormal function. The orthonormal function are given by phi 1 t is equal to under root 2 upon Ts into cos 2 pi Fct when t is between 0 to capital T, that is time duration, and phi 2 t is equal to under root 2 upon Ts sin 2 pi Fct, where small t is in between 0 to capital T. The equation 3 can be also written as Snt, that is equal to S1t into cos 2 pi Fct minus Sqt into sin 2 pi Fct, where Sit is in phase component, which is given by under root Es into under root 2 upon Ts cos phi t, and Sqt is quadrature phase component, which is given by Sqt, that is equal to under root Es into under root 2 upon Ts into sin phi t. We have to generate these signal in order to generate the QPSK signal. Now, next we will see the QPSK modulator. The block diagram of QPSK modulator is given by this diagram. Initially, we have a binary data sequence that will provide binary data and pass that data to NRZ, that is non-return to 0 encoder. The polar NRZ encoder generates the polar non-return to 0 signal regarding this binary data sequence. Suppose the binary data sequence is 0, 1, 0, 0, 1. Then the polar NRZ encoder will generate the negative voltage for binary bit 0, and for binary bit 1 it will generate the positive voltage. Then again for 0 it is the negative voltage and then positive voltage. So, here we get the signal. Polar NRZ encoder is applied at the demultiplexer input. The demultiplexer will split the bits into two parts, A1T and A2T. It will going to pass all even numbers of bits like 2, 4, 6th position bit value to the first product modulator and all odd number of bits like 1, 3, 5th position bit value to second product modulator. The second input to the first product modulator is orthonormal basis function phi 1t, and second input to the second product modulator is orthonormal basis function phi 2t. We already discussed about the orthonormal function. Then the output of these two product modulator is provided to adder, which will provide QPSK signal, that is SNT. Please keep in mind that the modulated signal where the carrier frequency or orthonormal function is cos 2 pi fct is called as in phase component, and the modulated signal where the orthonormal function is sin 2 pi fct is called as quadrature component. This is the description of this diagram. So, the incoming binary data sequence is first transformed into polar form by a non-return to 0 level encoder. We have already discussed about that. Thus, the symbol 1 and 0 is represented by plus under root ES and minus under root ES respectively, where ES represents the symbol energy. The binary wave is next divided into two separate binary wave consisting of the odd and even number input bit using demultiplexer. This we have tried to explain in description of block diagram. The two binary wave output demultiplexer are denoted by A1T and A2T, which is mentioned that even bit and odd bit respectively. In signaling interval, the amplitude of A1T and A2T equals Sn1 and Sn2 respectively, where this Sn1 represents the amplitude of first bit in nth symbol and Sn2 represents the second bit of nth symbol of QPSK signal. Depending on the particular debit, this is being transmitted. The combination of these two bits is called debit. We have already seen that we have four possible symbols, that is 00, 01, 10 and 11. So, the combination of these two bits is called as debit or symbol. The two binary waves A1T and A2T are used to modulate a pair of quadrature carrier or orthonormal basis function, which is given by phi 1t, that is equal to under root 2 upon Ts into cos 2 pi fct for the duration 0 to capital T, and second orthonormal function is phi 2 t, that is equal to under root 2 upon Ts into sine 2 pi fct for the duration 0 to capital T. The result is pair of two binary PSK signals which can be detected independently due to orthogonality of phi 1 t and phi 2 t, and at last the two binary PSK signal are added to produce the desired QPSK signal. Now, next we will see the QPSK demodulator. These slides represent the block diagram of coherent QPSK receiver or demodulator. First, let us see the description of this block diagram. At the input side, we have the received QPSK signal, that is S of t, which will pass through the two product modulator, in which first product modulator have second input as carrier signal phi 1 t, which is given by under root 2 upon Ts cos 2 pi fct, and which is nothing but in phase basis function, and the second product modulator have second input as carrier signal phi 2 t, which is given by under root 2 upon Ts sine 2 pi fct, and both the product modulator have same input from S of t as first input. The output of product modulator is passed through the integrator. Let the integrator 1 output is x1 and integrator 2 output is x2, which is passed through the decision device. If the value of x1 is greater than 0, then it will take the decision 1, and if the value of x1 is less than 0, then it will take the decision 0. Similarly, in second decision device, the value of x2 is compared with threshold value 0, and if the value of x2 is greater than 0, then decision will be 1, and if the value of x2 is less than 0, then decision will be 0. Then after that, these two bits will be combined with the help of a multiplexer, and the output of multiplexer is the desired bit stream as we transmitted from QPSK modulator. In this way, we will recover the binary transmitted signal from QPSK signal. This is the description of QPSK demodulator block diagram. Now, this particular slide showing the brief description of the whatever we had discussed so far in our last slide. These QPSK receiver consist of a pair of product modulator with common input and supplied with a locally generated pair of coherent reference signal phi 1 t and phi 2 t. The product modulator output x1 and x2 produced in response to the received signal S of t are each compared with a threshold of 0. If x1 is greater than 0, a decision is made in favor of symbol 1 for the in phase channel output, but if x is less than 0, a decision is made 0 in favor of 0, and if x2 is greater than 0, a decision is made in favor of symbol 1 for quadrature channel output, but if x2 is less than 0, a decision is made in favor of 0. Finally, these two binary sequences at the in phase and quadrature channel output are combined in a multiplexer to reproduce the original binary sequence. Now, next we are going to discuss some advantages and disadvantages of QPSK signal. Some of the advantages are, it has very good noise immunity, that is noise is not going to affect into greater extent. The second advantage is baud rate is half of the bit rate. In short, bit rate can be defined as number of bits transmitted per unit time, whereas baud rate is number of symbols transmitted per unit time. For BPSK, bit rate and baud rate both are same, but in QPSK, baud rate is half of bit rate. Next advantage of QPSK is it have low error probability, that is transmission quality is very good. The disadvantages of QPSK is the generation and detection of QPSK signal is quite complex as it require many components like multiplexer, demultiplexer, integrator, product modulator, etc. Now, the applications of QPSK. QPSK is used in satellite transmission of MPEG-2 video transmission, that is basically a signal compression format used for satellite communication. Next application is Iridium is a lower earth orbit satellite communication system which is used in QPSK. Next is in cable modems we are using QPSK. In CDMA system also we use QPSK signals, and some other form of digital communication also uses the QPSK signal. These are the certain application area where we are using QPSK. Now, let us see the comparison of quadrature phase shift keying, that is QPSK, with binary phase shift keying, that is BPSK, with some parameter. The first parameter is modulation technique. QPSK uses 4 distinct or different phase shift, that is 0, 90 degree, 180 degree and 270 degree to represent 2 bits of data per symbol, that is 00, 01, 10 and 11, whereas BPSK uses 2 different phase shift, that is 0 and 180 degree to represent 1 bit of data per symbol, that is 0 or 1. The second parameter is data rate. QPSK transmits 2 bit per symbol, which means it has a higher data rate compared to BPSK for the same symbol rate, whereas BPSK transmit 1 bit per symbol, resulting in lower data rate compared to QPSK. The third parameter is bandwidth efficiency. QPSK signal is more bandwidth effective as it transmits twice the number of bits per symbol compared to BPSK, whereas BPSK is less bandwidth efficient because it transmits fewer bits per symbol. The next parameter is bit error rate. QPSK signal generally has a higher bit error rate compared to BPSK under the same signal to noise ratio conditions, because it must distinguish between 4 phase states, whereas BPSK has a lower bit error rate than QPSK for the same signal to noise ratio, since it only needs to differentiate between 2 phases, making it more robust in noise environments. Next parameter is complexity. QPSK is more complex to implement, requiring more sophisticated signal processing to generate and detect 4 phase state, whereas BPSK is simpler to implement with lower computational complexity as it only involves 2 phase states. Next, we will compare BPSK and QPSK in terms of power efficiency. QPSK is slightly less power efficient due to the closer spacing of phase states, making it more susceptible to noise, whereas BPSK is more power efficient because the larger phase separation, that is 180 degree, makes it easier to detect a symbol, especially in low power or noisy scenario. Now, we will compare application of BPSK and QPSK. QPSK is commonly used in a system where high data rates are needed, such as Wi-Fi, cellular network, satellite TV, whereas BPSK is used in application requiring high robustness and simplicity, such as satellite communication and deep space communication. These are the comparisons of QPSK and BPSK. Now, last is the conclusion part. QPSK plays a pivotal role in the evaluation of digital communication, providing a foundation for more advanced modulation scheme. QPSK is widely used digital modulation technique that offers a balance between the data rate and bandwidth efficiency. Its ability to encode 2 bits per symbol makes it a more popular choice for various communication systems, including satellite communication and wireless network, etc.